Since we can view vectors as specialized matrices, just like adding two matrices together, we can add two vectors together. Let's say vector u is 1, 2, 3, and vector v is 6, 7, 4. Then the vector comprised of vector u plus vector v is 1 plus 6, 2 plus 7, 3 plus 4. You won't need to lay that arithmetic out like that. I'm just including it here because I want you to see what's involved in adding two vectors together. I've taken the first component of u and the first component of v, and that makes the first component, added them together, and that makes the first component of u plus v. So I'll simplify that quickly. That's going to be 7, 9, 7. And that's it. That's all there is to it. Let's throw another vector in here. Let's call it vector w. And I'm going to make this one be 5, 0. I can't do u plus w or v plus w because I'll just stick with one of these. I'll just do u plus w. Since vector addition means taking the first component of the first vector and adding it to the first component of the second vector, 1 plus 5 is 6. And then the second component and the second component, 2 plus 0 is 2. And then the third component with the third, there is no third component here. So there's nothing to add this third component to. So it's important that the vectors that you're adding together have the same number of components. So you can only add together 3-component vectors with other 3-component vectors. You can only add together 2-component vectors with other 2-component vectors. So w plus y will be 6, 7. That works, but y plus v or v plus y does not. Notice that because we're adding together the entries one at a time, right? We're adding together the first components and then the second components and so on. And because those components are real numbers, it's an interesting thing to note that u plus v, assuming that's defined, which in this case it is because they're both 3-component vectors, that's equal to v plus u. So vector addition specifically is commutative. You can do it in either order. Vector subtraction is very similar. I'll use the same vectors as I have here. I'll do u minus v, and that's going to give me 1 minus 6, 2 minus 7, and 3 minus 4. Again, I won't expect you necessarily to write that out like that, but I want you to see where these numbers are coming from. Okay, so there's u minus v. Let's do v minus u. That's going to be 6 minus 1, 7 minus 2, and 4 minus 3. And that is positive 5, and positive 1. So u plus v does equal v plus u, but u minus v does not equal v minus u. And again, that goes back to the fact that we're operating on the components, and the components are real numbers. You can add two real numbers together in any order, but you can't subtract because you get a different value. Well, in this case, you get different entries. Yes, they're only different by a sign, but these are away from each other on the real number line by 10, right? So they're very different values. These are away from each other on the number line by 2. So you be careful when you're subtracting two vectors to make sure that you're subtracting them in the right. Now, subtraction is really just addition of the opposite, and we could think of this way since we're just adding and subtracting the components one at a time, component-wise addition and subtraction. Let's let vector v be, I'm just going to go with 1, 2, 3. something nice and straightforward. Then -1 times v is negative v, which is -1 times 1, -1 times 2, -1 times 3. So I can think about negating a vector by multiplying it by -1. -1 is the scalar. That's just a scalar, and multiplying it component-wise, I'm multiplying it through the vector. So if I had, for example, let's put another vector up here, w equals 2, 0, 5, then I can write v as, I can write w minus v as either 2 minus 1, 0 minus 2, and 5 minus 3, which would be 1, -2, +2. Or I can write w minus v as w plus -v. And now I'm working with this vector here, not this one up here. I'm going to add these numbers to vector w. So I'm going to get w, the first component in w is 2. The first component in -v is -1. So I get 2 plus -1, which is 1. And then I get 0 plus -2 and 5 plus -3. So as you can see, you end up with the same vector, whether you consider subtraction directly or by adding the opposite. The point I'm trying to make here is that we're working with component-wise, we're working with real numbers, so I can subtract two numbers or I can add the opposite. But the next point that I want to make is that what this version of this subtraction is really a combination of addition, w, plus a scalar multiplication of another vector. So I could also write, for example, w plus 2v. And that would give me, see, the first component for w is 2, and I'm going to add 2 times the first component in v, 1. I'm working with positive v this time, but instead of scaling it by -1, where is that? Instead of scaling v by -1, I'm scaling it by 2. Let me write it down here. 2v is going to be 2, 4, 6. And that, in this case, is what I'm adding to w. So I have 2 times the first component of v, which is 2, plus the first component of, added to the first component of w. And for my second component, I'm going to have the second component of w, which is 0, plus 2 times the second component of v, which is 2. Or I could just directly take the second component of 2v, right? That's really what's going to happen here. The second component of v is 2. The second component of 2v is 2 times 2, or 4, right? So I could take it directly from there. The last one, the third component of w is 5, and I'm going to add 2 times the third component of v. And that ultimately gets me 2 plus 2, 0 plus 4, and 5 plus 6. So you can add together two vectors or subtract two vectors, or you can add together two scaled vectors. Like you can add together a vector plus another vector that's been scaled first. And the order of operations applies here because, again, inside vector v, we're working with the components that are real numbers. So when I multiply those real numbers, I need to do that multiplication before I add them to other real numbers. So order of operations that we're familiar with works. Let me do one more example. If I have vector A equals 1, 3, and vector B equals -1, 2, then I can write, for example, 5a minus 2b, which is going to be 5 times the first component in A minus 2 times the first component in B, comma, 5 times the second component in A minus 2 times the second component in B, which ultimately gives me 5 plus 2 and 15 minus 4.